Have you ever thrown a stone as far as you could? Have you ever pedaled until your legs gave out on a day so tiring that not even going downhill helped anymore? Have you ever seen a ball roll on the grass and stop by itself without anyone touching it? Nothing you set in motion keeps that speed forever. The bicycle slows down until it stops on the sidewalk. The ball slows down until it comes to a stop on the damp grass. A car without gas slows down and stops on the shoulder with the engine off. Only one thing in the entire known universe never does that. A light leaves a galaxy 13,800,000,000 years ago, long before any planet in the solar system existed. It travels through the vacuum with nothing to slow it down, no one to push it, for a length of time your brain can't really imagine. It reaches the telescope today at exactly the same speed as at the very first moment of its journey. Not even a little slower, not tired, not worn out by the journey. Exactly the same. This was never a story about light. That sentence will come back, and the second time, it won't mean exactly the same thing anymore. The question isn't why light is so fast. Almost everyone has already asked themselves that question, and it's almost boring. The real question, the one that occupied Einstein, the one Richard Feynman used to ask his students at Caltech, asking them to identify what was wrong with their own intuition is, why can't it do absolutely anything else? What stops it, even just once, from slowing down? 299,299,792.
2400
M/S. That's the number you've probably already heard in a documentary, in a class, somewhere, without anyone really explaining what it means. A number by itself describes, but doesn't explain anything. It doesn't say why this number, exactly this one, and not another, bigger or smaller. Here's what really bothers you when you look closely. A lot of things in the universe are fast. What makes light different is something else. The total inability to be anything other than fast, at that exact speed, with no exceptions and no room for negotiation. A rock can go fast or slow, depending on how hard it's thrown. A rocket can speed up or slow down, depending on how much fuel is left. Light, on the other hand, never had a choice. From the moment it exists, it travels at that speed, and nothing else is possible for it. 3 ways to say the same thing, because it deserves to be repeated before being explained. Light never slows down. Light never had a choice. And what you call the speed of light probably doesn't belong to light. The answer deserves to be built from the ground up, carefully, not just stated. Nothing slows down by itself. A bicycle doesn't stop because its movement would run out on its own. That old, false idea took centuries to disappear from people's minds, and Galileo dedicated a good part of his work to this, against the almost unanimous opinion of the philosophers of his time. A bicycle slows down because something is braking it. The air hitting it, the ground rubbing against it, gravity pulling it down whenever there's an uphill stretch. Removing all these brakes, an object in motion would continue indefinitely, at the same speed in the same direction. This is the principle of inertia. A space probe launched into the vacuum, far from any planet, keeps moving forward without any engine ever turning on again. No one pushes it, nothing slows it down either, and it keeps going indefinitely, at the same speed, in the same direction. So maybe light also moves like that, simply in the vacuum, with nothing to slow it down. That's the full explanation. Almost. There's one essential piece missing, and that's where it gets interesting. A space probe could, in theory, go slower. It would just need less fuel at launch. It could also, in theory, accelerate even more with a more powerful engine, if engineering allowed. Nothing in its nature forces it to travel at a specific speed. Light, on the other hand, couldn't go any slower, even if the entire universe asked for it. It simply has no reason to slow down. It doesn't have, inside it, literally anything that could slow it down. Here's the reason. Slowing down, speeding up, braking, all of that requires a specific physical property: mass. Mass isn't just the amount of matter you learn about in school. In physics, mass is resistance, a resistance to a change in speed. The more mass an object has, the harder it is to make it go faster or slower. That's why it's easier to push a bicycle than a truck. The truck resists change. It has inertia. And the bicycle, almost none. Photon, the grain of light, has no rest mass. Zero. Not even a small amount of mass. Zero. In all measurements made so far, with extreme precision. An object without mass has nothing to oppose a change in velocity. No resistance, no inertia. Which means, quite concretely, that a photon cannot be pushed faster nor held back to go slower. It is never born slow to accelerate later. It only exists at a single speed from the very first instant, without a start and without any push. It is or it isn't, and when it is already born at the limit. Physicists have known this for a long time, but knowing that a photon has no mass still doesn't explain why this exact speed is the limit for the whole universe, and not just for light. To understand this, we need to go back to a series of observations made from Paris in 1676. The Danish astronomer Ole Hammer spent his nights at the Paris Observatory timing the eclipses of one of Jupiter's moons, and what disappears and reappears behind the planet with a regularity that astronomers of the time compared to a celestial clock, something that could be used to calculate longitudes at sea. These eclipses occurred almost exactly at the predicted time, but not exactly. In certain months, the eclipse arrived later than predicted, in others, earlier, and no one understood why. No one could explain why the celestial clock, considered the most reliable of all, would become irregular like this, month after month, without any apparent reason, year after year of careful observations. Hammer noticed a detail that others had overlooked. The delay appeared when the Earth was moving away from Jupiter in its orbit, and the advance happened when it was getting closer. From that, he came up with a bold hypothesis for the time. What if there was nothing wrong with the celestial clock? What if it was simply the light on its way from Io to Earth that took time to arrive, a little more when the distance increased, a little less when it decreased? The idea seems obvious today. In 1676, it was not obvious at all. Until then, many scholars, including prominent names in Parisian astronomy, believed that light was instantaneous, present everywhere, at the same time without any delay, no matter the distance traveled. Romer had just demonstrated, through careful observation over several years and patient deduction, that light takes time to travel. According to his estimate, it takes about 10 to 11 minutes to cross a distance equal to the radius of Earth's orbit. It still wasn't an accurate measurement of the speed. It would come later, in 1849, with Hippolyte Fizeau, who achieved the first entirely terrestrial measurement. He made a beam of light travel the distance between Suresnes and Montmartre, passing through the teeth of a wheel spinning at high speed, measuring at which rotation the returning beam was blocked by the next tooth. But Romer, long before him, had already opened the door. Alone, in the observatory, with a telescope and years of patient notes as his only instruments, light is not instantaneous. It travels. It has a speed.
And once you know that it has a speed, a much more troubling question starts to arise. A speed relative to what? That's exactly the question that 19th century physics thought it had solved, and which a failed experiment in 1887 blew to pieces.
At that time, almost all physicists thought that light, like sound, needed a medium to propagate. An invisible and motionless substance filling all of space, called ether. The Earth, revolving around the sun, would necessarily have to move through this ether, kind of like a swimmer moves through water. And if that were true, the speed of light measured on Earth should vary slightly depending on the direction. Faster in one direction, slower in the other. Exactly like a swimmer's speed changes depending on whether he's swimming with the current or against it. In an old and silent library, Albert Michelson and Edward Morley built in Cleveland a precision instrument never seen before, an interferometer mounted on a stone block floating in a tub of mercury. So they could rotate it without the slightest parasitic vibration coming from the building or the floor. They measured the speed of light in all directions, again and again, day and night, at different times of the year, to make sure they would cross the ether current at every possible angle. At some point during the experiment, they found nothing. No difference in any direction at any time of the year. The light traveled at exactly the same speed. Always, always. As if the Earth wasn't moving through absolutely nothing, which went against everything that was expected from physics up to that point. An experiment that finds nothing shouldn't go down in history. This one did, because the nothing it found was impossible to explain with the known laws of that time. For almost 20 years, no one knew what to do with that. Some invented increasingly complicated explanations to save the ether. Theoretical patches upon patches. None of them held up, and the result remained there, intact, like a piece that doesn't fit into any known puzzle. It was Einstein, in 1905, who drew the simplest and most radical conclusion. What if there was no ether at all? What if the speed of light was simply the same for everyone, all the time, no matter the observer's speed? Not because some complicated mechanism forced it, but because it's a basic property of the universe itself. This is where the name speed of light starts to become misleading. And maybe it's time to admit something. The expression cosmic speed limit, which appears in almost every documentary, doesn't completely convince me. It sounds like a rule imposed from the outside, a kind of sign stuck somewhere in the vacuum, when in fact no one imposed any limit at all. The structure of space and time constitutes this limit, kind of like a circle doesn't choose to have a constant radius from the center. It's simply what it means to be a circle. Here is the central idea, and it deserves to be said in full. The speed you call the speed of light is not a property of light. It's the maximum speed at which one thing can affect another. No faster anywhere, ever. Among physicists, it's sometimes called the speed of causality, the maximum rate at which a cause can produce an effect anywhere in the universe. An explosion on a star light years away from here will never be able to reach you, not even indirectly, before that limit is respected, no matter how urgent the information seems. No known force, no signal, no information has ever found a way to get around it, despite more than a century of theoretical attempts to find a loophole in this rule. This was never a story about light. The most beautiful proof of this idea doesn't even need light. On August 17, 2017, two detectors in the United States and Italy, belonging to the LIGO and Virgo collaborations, detected, almost at the same instant, a tiny vibration of space itself. A gravitational wave produced by the collision of two neutron stars about 130 million light-years away.
Anos-luz da Terra.
A gravitational wave has nothing to do with light. It's a deformation of space-time, a wrinkle in the fabric of the universe, produced by immense masses colliding with each other. And it passes through matter almost without ever interacting with it, unlike light, which bumps into everything in its path. About a second and 7/10 after that wave, a tiny delay. After a journey of about 130 million years, telescopes all over the world detected a gamma-ray burst coming from exactly the same place, produced by the same event. Two completely different phenomena. One made of pure gravity, the other made of light. They left from the same point, at the same instant, after a 130 million year journey through the vacuum, and arrived practically together. The exact same speed, with a precision that no earthly laboratory could directly test. If the speed called the speed of light really belonged to light, nothing would force a gravitational wave to obey it as well. They are two completely different messengers, sent by the same event, and they ran the same race, exactly tied, over 130 million light-years. The only explanation that holds up is that this speed doesn't belong to either one or the other. It belongs to space-time itself. Light and gravitational waves are only obeying a limit that already existed before them, and that would continue to exist even if they didn't exist. This event marked the beginning of what astrophysicists today call multi-messenger astronomy, observing the same cosmic phenomenon through several completely different channels. Light in all its forms on one side, the vibrations of space-time on the other, comparing what each one tells us about the same moment. Before 2017, gravity and light had always been studied separately, with separate instruments, separate teams, and scientific traditions that hardly interacted with each other. On that day, for the first time, the two accounts overlapped almost perfectly, at a distance that makes the exercise almost impossible to imagine. Two messengers, leaving at the same instant from a galaxy 130 million light-years away, compared with less than 2 seconds of difference. Upon arriving on Earth, after a journey that began long before any human being existed to measure it, the physicist Etienne Klein describes a similar principle in one of the books he wrote about the physics of time, published in 2003. Special relativity doesn't just say that nothing goes faster than light. It protects something deeper, the very order of causes and effects. If information could travel faster than that limit, it would become possible, in certain situations, for the effect to precede the cause itself, which simply makes no sense in a coherent universe. The limit is not arbitrary. It's what prevents the universe from contradicting itself. Light just obeys this limit. If light didn't exist, the limit would still exist. If light can't pay the debt with speed, it has only one possible currency left: energy. And that's exactly what it does, quietly, all the time, without ever slowing down a single meter per second. The light from the sun illustrates this mechanism well. It leaves the surface of the sun at its usual speed, crosses the sun's gravitational field to escape it, and reaches you. Slightly redder than when it left. Not slower, folks. This light effect is called gravitational redshift, a tiny loss of energy, about 2/1,000,000th of the original frequency, but real. Measured, predicted with extreme precision, since experiments conducted in the 20th century in laboratories that managed to detect a difference as small as this. The fairest comparison is that of a stone thrown upwards. It can't stop moving halfway up, but it loses speed as it goes up until it reaches the highest point. Light, on the other hand, can't lose speed, so it loses something else, energy. The stone pays with speed. Light pays with color. Taken to the extreme, this same mechanism gives rise to a black hole, where the speed needed to escape gravity exceeds the speed itself. Of light, the toll becomes infinite. The light that tries to escape loses all its energy before it can, becomes infinitely red, literally invisible, and then nothing. No wall prevents light from escaping a black hole. Nothing blocks it. No surface, no barrier, no material boundary of any kind. Nothing you can touch or draw on a diagram. It tries. It pays. And the price gets so high that there's not enough energy left to exist in an observable way. That's why a black hole is black. Not because something prevents it from being bright, but because the toll is so high that the light can't survive all the way out, no matter how many times it tries to escape. The intuition that gravity should be able to hold light isn't actually wrong. It's exactly right. What most objects in the universe lack is simply enough gravity to make the toll infinite. The sun reddens its light only slightly as it leaves. It is neither massive nor compact enough to do more than that. There is a third way to make light pay, even stranger, because it doesn't come from a star or a black hole, but from the entire universe. Space itself has been stretching continuously for 13 billion and 800 million years. A wave of light traveling through stretching space stretches along with it. The wavelength increases, the energy decreases, always without the speed changing by a single meter per second. The oldest light accessible to telescopes, that cosmic background radiation that astrophysicists talk so much about, left its origin about 380,000 years after the beginning of the universe, when it was still visible light, almost white, the kind that an eye, if it existed there, would have been able to see. After 13 billion years of stretching, it arrives today as microwave radiation, with a wavelength about 1,100 times greater than when it started, completely outside the spectrum that any human eye can detect. It never slowed down. It aged to the point of completely changing category, going from a light that the eye could have seen to a signal that only an antenna can pick up today. Maybe that's the fairest thing you can say about light. It never slows down, but it ages. Every photon that reaches you is just a little poorer than the one that left. There is a point where this story seems to contradict itself, and it's worth clearing that up before moving on, even if just briefly. Water, glass, or any other transparent object that light passes through every day before your eyes. A stick half submerged in water looks broken, bent at the surface, as if the submerged part had changed angle on its own. The explanation you hear everywhere, in most textbooks and educational videos, is that light slows down inside water. For a long time, I accepted that statement without really understanding it, kind of like accepting a formula without questioning the mechanism. Until I reread several times the chapter from Feynman's physics courses dedicated exactly to this question. Chapter 31 of the first volume, published in the early 60s. What Feynman explains, patiently, is that between the atoms in the water, in the vacuum that separates them, light continues to travel at exactly the same speed as always. What slows down is not the light itself, but the signal as a whole. Each atom that light passes through absorbs a tiny part of that luminous energy and re-emits it almost instantly in all directions. The wave that comes out of the water is the sum of the original wave and billions of these micro re-emissions. That combined wave travels just a little slower than the original light, because each re-emission adds a small delay. But between two atoms, in the vacuum that separates them, no photon has ever slowed down by even a single meter per second. It's not the light that slows down. It's the interaction between light and matter that takes time. This mechanism deserves a video of its own, and it's not this one. The fundamental speed, that one never changes, even when everything seems to indicate otherwise. The sun has been shining for about 4,600,000,000 years. Every second of each of those years, it has emitted light in absolutely all directions at the same time. Not only toward the 8 planets of the solar system, but toward every possible point on a sphere in a vacuum without exception. Seen from the sun, the Earth occupies such a tiny portion of the sky that it's almost funny, much less than 1/10 of a millionth of the entire sphere that the sun illuminates at any given moment. Such a tiny target that most of the rays would simply never have a chance to hit it, which means, quite concretely, that the overwhelming majority of the light ever emitted by the sun has never encountered the Earth, nor any other planet, nor any star, nor anything at all. It traveled through the vacuum in a direction where there was nothing to touch, and it keeps going, even now, without having slowed down. At no point since it was emitted has it changed its trajectory or lost any of its initial energy, except for this slow aging caused by the expansion mentioned earlier. For every photon that ends its journey in a human eye, on a plant leaf, or on the surface of a distant planet, there is an almost incalculable number of other photons that left at exactly the same moment from the same star, condemned to never touch anything. Never, never. Not in 1,000,000 years, not in 1,000,000,000 years, not even after the sun itself has gone out. They travel distances that surpass any galaxy, and they'll keep doing that for billions of years, unless by pure chance they cross something in their path. A speck of dust, a planet, a telescope pointed at the right place at the right time, among trillions of possible directions, where there was absolutely nothing waiting. There's an irony in all of this that few people notice. Even before reaching open space, where it can finally travel without obstacles, the light born at the center of the sun first needs to cross the sun itself. And this crossing is almost comically slow, in complete contradiction to everything that was just said about a speed that never changes. Inside a star, the matter is so dense, so compressed by its own weight, that photon, born in the core of the sun, is absorbed and re-emitted, again and again, in a random direction each time, before finally reaching the surface. A bit like someone trying to find their way out of a huge crowd, constantly bumping into other people, changing direction with each collision, never able to go straight for very long. Estimates vary. Some calculations say tens of thousands of years, others say much longer, and no one has a definitive number, because the exact path depends on assumptions about the sun's internal structure, which are hard to verify directly from the outside, since no one can simply open up a star to look inside. What is certain is that photon, which warms your face today, probably began its journey inside the sun, long before any human civilization existed on Earth, even before the first complex form of life appeared in Earth's oceans. Then, once finally released at the surface, it took just over 8 minutes to travel the rest of the way to you, through the vacuum, at the same unchanging speed as always. An endless birth, followed by an almost instantaneous journey through the vacuum, on a human scale. The
Astrophysicist.
Hubert Reeves.
In one of the books he wrote about cosmic evolution, published in 1981, he dedicates an entire chapter to a seemingly childish question, the kind a child would ask, and that adults rarely stop to truly answer. Why is the night dark If the universe contains hundreds of billions of galaxies, each one full of stars that shine non-stop. His answer gets exactly to the point of what's at stake here. The night sky isn't dark because of a lack of light. It's dark because most of that light, even from the nearest stars, still hasn't had the time or opportunity to reach our eyes. And the light coming from the farthest reaches of the observable universe will never make it, because the space between it and the eyes stretches faster than it can travel.
Maybe that's the best definition of what it means to see something. Light only exists for someone at the exact moment the journey ends, when it is absorbed by an eye, a sensor, a leaf, a stone. Before that moment, it is seen by no one, experienced by no one. It simply travels in the dark at its unchanging speed. And that would also explain why the space between the stars seems so dark. Not because it's empty of light. Trillions of photons pass through it every instant in all directions. It's dark because that light is just passing through there. The void is not the absence of light. It's light that hasn't found anyone yet. There's one last question left, the strangest of all, and it requires you to step outside your own Earth-based point of view for a moment. A ray of light that left a galaxy 13 billion years ago took 13 billion years to arrive.
No one disputes that. But from the point of view
Of the very
photon itself, if a photon even has a point of view, which is already a delicate question, this journey didn't last any time at all.
zero.
Not even a fraction of a second. The departure and the arrival are, for him, one and the same instant.
That's not a poetic image at all. It's a direct consequence of the equations of special relativity. The closer an object gets to the structural limit of the universe, the more time measured from its own frame of reference slows down, until it stops completely, exactly at that speed. An object traveling at that limit no longer experiences the passage of time. Emission and absorption become simultaneous for it. Here, honesty becomes necessary, and it's better to state this clearly than to just let it slide. Saying what a photon feels already pushes language beyond what it can actually describe. And no serious physicist would use that phrase outside of a popular science context. Special relativity defines a reference frame, a point of view consistent with proper measurements of distance and duration for any object that moves slower than the limit, no matter how close it is to that limit. It doesn't define any for an object that travels exactly at that speed. The equations literally stop working at that exact speed, producing divisions by zero instead of usable answers. There is no such thing as a photon's point of view in the proper sense of the term. And no serious physicist claims that, no matter how tempting it is to use that image in an explanation. What physics can state with certainty is that the very notion of duration collapses at that speed, and it is not reasonable to go much further than that in the description. It's not a door that's closed for lack of courage or method. It's a door that mathematically doesn't exist in the theory as it is formulated today. I haven't looked at the night sky the same way since this idea really settled in for me. Before, a star was a fixed point, ancient, distant, almost decorative, just part of the scenery and nothing more. Now, each point of light seems more like the end of a journey than an object. It's no longer just ancient light coming from far away. It's a journey that, for the light itself, never had any duration, and that only ended at the exact moment when a human eye or a telescope caught it. Before that moment, this journey didn't exist for anyone. It didn't really exist for itself either. So maybe that's what this story is really about. A light coming from a galaxy that's 13 billion years old didn't take 13 billion years to reach you. It simply existed once there and once here. Nothing between those two moments. And what fills that void between the two isn't time. It's you. Looking. This was never a story about light. It was a story about causality from the very beginning. The rhythm at which the universe allows one thing to touch another. Light is just its fastest messenger, unable to lie about the length of the journey, since it has never crossed any itself. There is still much to explore in this same family of questions that remained unanswered today. Why would crossing this limit, in practice, mean going back in time? What does it actually do to the clock here on Earth that gets closer to it without ever reaching it? How does mass change, second by second, in its own passage through the future? You, who have mass, unlike light, and because of that, will never truly be able to reach it. Another light, in another video, to keep moving forward through this same darkness. The one that, like the emptiness between the stars, only waits to be crossed by someone who is watching.